Let's start with an introduction on why we chose to do this topic, or maybe you could call it a motivation. We know that in the recent years, we have seen amazing improvements and amazing performance of the black box algorithms like deep neural networks, transformers, and everything related to deep learning. But even though the performance is good, they have certain areas where they lack certainty and transparency. And I'm going to give you a few examples where this might be a problem. In certain sciences like chemistry or physics, having a model that can, for example, classify a compound just by giving it the structure is not that useful, because scientists usually want to extract some insight. They want to understand the world and why this specific compound behaves a certain way. So giving just a result without at least uncertainty or anything else is kind of useless for them. Another problem of these models is the lack of certainty. And in critical systems, we usually want to know that something is formally tested, or if we don't know that something will work, we want to know how likely it is to work, to have like a certain confidence intervals or maybe a distribution. And the third one would be lack of transparency, because users can't trust a system they don't understand. If they don't work in AI, deep learning, they won't understand what it does, and that could actually cause problems for certain businesses. If a user wants to know why this ad was recommended to them, you can't really give a justification, just this is what the algorithm gave us, and we passed it on. And this might also bring some legal issues because you can justify some decisions. This is why we wanted to do a white box model, to develop something like that can learn in a more transparent way. Let's go to the theoretical background. A very simplistic definition of ontologies is just a structured way of storing data and the relations within that data. And they have the following components: classes, which are like classes in any other field, like in math, in object-oriented programming. We have instances, which are like the actual thing in the world, not like a group. And we have certain relations between classes and instances. Maybe this sentence is a bit misleading, because we can have relations between classes and classes and instances, not only classes and instances. And like in the final component is called axioms, which are just statements or facts that impose a certain way that our ontologies can be created. Here we have like a visualization of an ontology. Here you can see the top class, thing. It's like a class that encompasses everything. Every instance is part of thing, with a relation of type subclass with the blue arrows, because we have two actual classes, male and female. With the purple arrow, we have an instance type of relation, because, for example, male has Stefan as an instance, and female has Michelle and others. And you can see also between instances dotted yellow arrow, which is the relation of has child. So if we look at this, for example, Anna is the child of Martin, or Martin has a child Anna. And here we have a few examples. We talked about the first three, but an axiom would be something like this. It's a logic proposition, logic expression, which tells us that a person has at most two parents. We put this axiom so we can prevent some unfortunate cases where we would insert 10 parents for a single person, which doesn't really make sense, or at least we could say it doesn't make sense in our use case. And why do we actually use these ontologies? Because they provide a shared formal understanding of a domain. If we have ontologies in chemistry, they can be shared between different institutes, different universities, and the data can be like structured in the same way and can be concatenated with the already existing information. A big part of what makes ontologies and description language which is the formal way of defining them important, is that we can query something that is not implicitly explained. For example, if we have a dog in our ontology, we can query for mammals, and since we know dogs are mammals, we will get the dog as an instance, even though it's not explicitly a mammal. And ontologies are not static; they evolve based on new knowledge. And scientists add knowledge to a certain ontology in their specific field, or to a top-level ontology, which is an ontology which defines processes, humans, very abstract and basic things. They are like the start of creating your own ontology in the specific domain. Description logic is what is actually used for querying and inference on ontologies. Why was this specific logic chosen and not others? Because there is a trade-off in logic between expressiveness and computational complexity. Propositional logic is very easy to actually compute. It isn't that expensive, but you can just express a few simpler things, not something very complex. On the other hand, the first-order logic is very complex. You can express a lot more, but it's very expensive to actually compute and do inference on it. So description logic is like the middle ground, where the trade-off is the best for the ontology use case. And what our algorithm will actually do is doing inductive reasoning, and that means from a few examples we'll get a description logic expression. Here are a few examples of description logic. We can have male be a part of person, so every instance of male will also be an instance of the class person. Equivalence, individual assertion, we can make Marcus a male like this, or we can do role assertion like this. Has child Marcus Anna. That would mean that Marcus has a child named Anna. Okay. The actual problem would be defined like this. We get a knowledge base, an ontology, and two sets of individuals. And we want to find a class expression or a description logic expression that best separates them. So as input, you would have the positive individuals that are part of that class or that would give us true when put through that expression. And the negative individuals, the knowledge base, which in our case would be an ontology, and some configurations file to choose between different things. And the output should be a set of class expressions and a metric for each of them. We'll see later how this would actually look. For example, in this small example, we have Stefan, Marcus, and Martin as positive examples, as noted in the P plus set. And Heinz, Sana, and Michelle in the P minus set, which are negative examples. So we need to find something that would, an expression that when we put the positive things through it, it would give us true and false for the other ones. We can see that one of the expressions found is male, which works for all three because all three in the positive are males, and works for Anna and Michelle, but not for Heinz. And this would be like 5/6, so this would be the accuracy. But with more computation and more searching, we can find male and has child. So why do we actually call these class expressions? Because we could use this male and has a child basically to create a new class called father and put these individuals in, and this will not be part of that class. And why would it would need this in a real scenario, not in this example, small example? One of the data sets is that is used for this to test this type of algorithms is actually called the carcinogenesis. And basically, if you have the structure of a certain compound, you can tell if it can create cancer or not. And you can do this by just searching for simple class expressions like this. Maybe a bit more complicated, but the idea is the same. DL Learner is a framework for description logic learning. We chose this because it's efficient, it has an active community and updates, and it's very modular in architecture. So it's easy to expand a certain algorithm or just a certain part of it without creating everything from scratch. And class expression learning for ontology engineering is like their best algorithm. I will just call this the base algorithm because this is the one that we used to, this is the one we extended to create our one forest mixing. And this is how the system would look like. We have just our example and ontology, and we put them through our new extension of the learner with a new algorithm for mixing. And we get as an output just some class expressions and some values for them, so we can know which one is better than the other. So how does this algorithm actually work? We choose a starting class. This can be thing, like the most generic class, or can be anything else. Let's say we choose the class student. We create a search tree, which is a tree in which we put all the expressions found. And then from there, we can create from a certain node. We can specialize that expression and find another and put it in a tree. So refining is basically specializing an expression. For example, student and university employee is a subset of student, a more restrictive one. And student and studies at Romanian university would be another restriction of the student. So there are like two different possible things to add. And we would choose the best one using a certain heuristic and add it to our search tree. And it would look something like that in the case that student and university employee is a better expression that would give us a better score than the other one. So that was like the base algorithm. And what does our approach gives us? Instead of starting with only one tree and continuing to create that tree, we use multiple search trees starting from totally different points in the ontology. And their refinements. Refinements are, again, the specializations of a certain node. We know the student covers all our positive examples, and we want to specialize this until it doesn't. So we have the most specific expression that also covers our examples. And these subtrees or small trees would create from their nodes the refinements, which are more specialized expression. And we would choose between them. Sorry. And we'll choose from a common refinement pool for each of them instead of choosing each individually. So we could use something like a conjunction or logical AND to combine the best from each tree to create even more interconnections between these trees. And what we think would be the possible advantage of this is when we have non-disjoint classes, or when we have an expression of the following kind, when you have your student and university employee are two different classes, and they might be very very different, might be very far away in the search tree. And it will take a long time to actually find those two and create an expression for those two. This is better exemplified in the following diagram. So this would be like the search space, the tree created in the original algorithm. We can see that between thing and student, there are a lot of classes. And between these two, there are also a lot of classes. And you need to cover basically this entire part to actually find a class expression that includes both of them to be somewhere here. You need to search in the entire tree. But when you use multiple search trees from starting from different nodes, it would have something like this where we start from student and university employee, and students and university employees like one of the first things we would try because we start from these two. No matter how far apart they are, how many nodes are between them, we would still, in theory, find relatively fast expressions which combine them. Now let's go to testing and see if that's actually true. So a test is basically an ontology used as background knowledge. Some class expressions, one class expression that is like the ground truth. So we know if we found the best one available, and our positive and negative examples. And we did 3 types of testing. Testing with real data, which is that carcinogenesis data set or problem that is used for this type of algorithms. Testing with an ontology manually constructed with non-disjoint classes. This is a really small one, maybe like 20 or so instances. And testing with synthetic data generated with this tool, University Ontology Benchmark. And this tool basically generates an ontology, and we find expressions of type class and has relationship to the top. Really simple expressions, but a lot of problems can be solved with these simple expressions, and we thought it was enough for this research. And the results. Okay, we have 3 columns with predictive accuracy, F measure, and time in minutes. Time is not really that important. We have our base algorithm on the second row. The first 3 are basically their algorithms from the framework. And the last 3 are our algorithm with different kind of heuristics for different problems. And here we can see that in our case, when using HT1 and letting it run a bit more than the others, it actually comes up with something better. But in reality, it's kind of close to the base algorithm, not a big difference. Another example is in the carcinogenesis set, which is the one tested here. Our algorithm found that it must be a compound that has 3 atoms of carbon-10. The testing on the non-disjoint classes. Here we used the number of refinements as a metric because refinements are the most computationally expensive part of the algorithm. So the less we need to specialize a class again, the better. And here, and this is on the non-disjoint set, so basically on the really small one that we thought our algorithm would work better on. But looking at the result, if you give the base algorithm a good starting class, it outperforms our implementation. And as a conclusion, in the general tests, our algorithm is about the same as the base one. In the example we thought would be better, it's actually worse. But our testing was one ontology with just a few expressions, and it was really small. So maybe the overhead of having multiple trees is the problem there, or maybe we need different heuristic for this kind of problem, or specific ones for different trees. And possible improvement would be a different implementation of these special heuristics for this problem itself, for different management of the pools of refinements. And also a good point would be some kind of parallelization. If you can actually isolate the trees without communicating with them, would be kind of interesting. This is all. Thank you very much.